The general form of the exponential function is given by the equation y equals a times b to the power of x, where b is base and x is exponent. Please make sure to check the conditions for a and b as well. Let's start by examining the parent function of exponential function, y equals 2 to the power of x. We'll make a table first. The domain will be selected as integers from 4 to 4 for simplicity. Let's plot the graph using the given data. The ordered pairs from the table are represented by red dots on the graph. Looking more closely at the graph, it's important to note that although the domain is limited to integers, the actual domain is all real numbers. As the graph lies above the x-axis, the range is always positive. And the x-axis acts as the horizontal asymptote, which is y equals 0. As x increases, the graph trends upward, indicating exponential growth. In this case, the base is greater than 1. Meanwhile, for the graph of y equals 1/2 to the power of x, as x increases, the graph trends downward, representing exponential decay. Here, the base lies between 0 and 1. Now, let's explore the relationship between these two graphs. If we substitute negative x for x in the parent function, we get 2 to the power of negative 1 to the power of x, which is equivalent to 1/2 to the power of x. It is reflected across the y-axis. Examining the different case, substituting negative y for y in the parent function results in y equals negative 2 to the power of x. It is reflected across the x-axis. One of the notable features of exponential functions, as observed earlier, is the rapid increase or decrease in function values as x increases. This characteristic is utilized in explaining various phenomena such as growth, decay, compound interest calculations, and material decay. Let's now delve into a representative exponential growth and decay model given by a t equals a times 1 plus or minus r to the power of t. A is the function value after time t. A is the initial value. R is the growth or decay rate. And t represents the number of time periods. Let's solve some example problems. The population of bacteria after 1 hour is 20. After 2 hours is 40. And after 3 hours is 80. Therefore, we can formulate the function as 10 times 2 to the power of t, where t represents time in hours. The growth rate r is 100% as the quantity doubles. Therefore, the growth factor, 1 plus r, becomes 1 plus 1 equals 2. Please understand this point well. When we graph this exponential growth function, depicted in red, the blue line represents the baseline of 10,000 bacteria. The coordinates of the intersection are 9.966 and 10,000. Consequently, it takes approximately 10 hours for the initial 10 bacteria to double every hour and reach a population of 10,000. Example 2, radioactive decay. After 100 years, it reduces to 10 times 1/2 to the power of 100 over 100. After 200 years to 10 times 1/2 to the power of 200 over 100. And after 300 years to 10 times 1/2 to the power of 300 over 100. Therefore, the function describing the decay is 10 times 1/2 to the power of t over 100. The decay rate r is 50% as the quantity halves. Therefore, the decay factor, 1 minus R, becomes 1 minus 0.5 equals 0.5. In the above formula, plus or minus is applied based on whether it is an increase or decrease situation. Please understand this point well. When graphed, depicted in red, the blue line represents the baseline of 1 gram of the radioactive material. The coordinates of the intersection are 3.322 and 1. Hence, with a half-life of 100 years, it takes approximately 332.2 years for the initially 10-gram radioactive material to decay to 1 gram. See you next time.